All right, buckle up, everybody, because today we are diving headfirst into something truly mind-bending.
Oh, yeah.
Loop quantum gravity,
That's right.
LQG, for those in the know. It's one of those theories that tries to make sense of the universe at its most fundamental level.
Yeah, exactly.
And frankly, sometimes trying to understand it feels like learning a whole new language. Am I right?
Absolutely. It can really feel that way.
It really can. And it can
Yeah.
quickly slip into, jargon that even physicists struggle with, I imagine.
Absolutely.
But the good news is the core idea is pretty straightforward, right?
Yeah, it really is.
So tell me, in a nutshell, what is LQG trying to tell us about how the universe works?
So the big idea is, what if space and time, the very fabric of reality as we experience it,
Yeah,
aren't smooth and continuous like we tend to assume?
right.
What if, at the tiniest level imaginable, they're actually made of tiny, indivisible chunks?
Okay, I'm already intrigued.
Yeah.
It's almost like saying the universe is pixelated in a way.
Yeah, in a way.
But how on earth do you even begin to picture something like that?
Mm.
It goes against everything our senses tell us.
It absolutely does, and that's where analogies are really helpful.
Okay.
So think about it this way. Imagine trying to make a smoothie, but you can only use these giant chunks of fruit.
Okay.
You're not going to end up with that smooth, creamy blend that you're looking for.
More like a fruit salad than a smoothie.
Exactly. More like a fruit salad.
Okay, I think I see where you're going with this.
Right. So in classical physics, we treat space-time like that perfectly smooth smoothie.
Uh-huh.
It's based on Einstein's theory of general relativity,
Right.
which works incredibly well for large scales, for planets, stars, galaxies.
Right, the big stuff.
The big stuff. But when we try to apply it to really extreme situations,
Okay.
like the singularity of a black hole or the very beginning of the universe, the Big Bang,
Right.
things just start to break down.
It's like trying to make that smoothie, but your blender isn't powerful enough to handle those massive chunks of fruit.
That's a perfect way to put it.
Okay.
So that's where OQG comes in.
All right.
It says that at these incredibly tiny scales, what we call the Planck length,
Right. Planck length.
space-time itself is granular, like those chunks of fruit.
So there's a limit to how finely you can divide it.
Exactly. You got it.
Planck length, I feel like we've talked about this before, but just remind me, how small are we talking here?
Oh, it is mind-bogglingly small.
Yeah.
It's about 10 to the power of negative 33 centimeters.
Okay, that's like...
To give you some context, if an atom were the size of our solar system,
Wow.
the Planck length would be like the size of a tree.
Okay, yeah, I'm officially feeling microscopic.
Right.
So we're talking like space-time at that scale is almost like a mosaic then, with each tile being a Planck length across.
Yeah, that's the general idea. But instead of tiles,
Okay.
LQG proposes that the fundamental building blocks of space-time are actually loops.
Loops.
Loops, yeah.
Okay.
And these loops are formed by the gravitational field itself. And they kind of weave together to create that fabric of space-time.
So wait, hang on, loops.
Loops.
Not like tiny vibrating strings like we hear about in string theory.
Right. That's a really key difference between these two approaches to quantum gravity.
Okay.
String theory says, everything is made of these tiny vibrating strings, but LQG takes a different route and says, no, it's all about these loops
It's all about the loop.
of gravitational energy.
Okay. So help me wrap my head around this.
Sure.
How do these loops actually create what we experience as space-time?
So imagine these loops as like threads in this giant cosmic tapestry.
Okay.
Each loop has certain properties,
Yeah.
kind of like the thickness or the color of a thread.
I like that.
And the way these loops connect and interact with each other
Uh-huh.
determines the geometry of space-time at that Planck scale.
So each loop is kind of contributing its own little bit to the overall curvature and shape of space-time.
That's a great way to put it.
Okay, my brain is definitely doing loop-to-loops right now,
I can imagine.
but I'm trying to follow along here.
Yeah.
So we've got these loops,
Yeah.
and then what's it called? A spin network, right?
Yes, a spin network.
Describes how they all connect together.
Exactly. That network of loops is what we call a spin network. And it describes the quantum state of space-time at that incredibly small level.
Okay, spin network, got it. But what does spin have to do with anything?
It's all about angular momentum.
Okay.
Each of these loops carries a certain amount of angular momentum, and we call that spin in the quantum world.
Right.
And this spin determines how the loops connect and interact within the network.
So essentially, the spin of each loop affects how it kind of fits into the overall tapestry.
Exactly. You got it.
All right, this is where I think I need you to slow down just a little bit for me.
Of course.
So we've got these loops.
Right.
They form this network,
Yeah.
and their spin affects how they interact.
Mhm.
But how does all of that actually translate into the space-time that we experience, the world that we live in?
This is really the heart of LQG. And it's saying that all the properties of spacetime, its curvature, its expansion, even the flow of time itself,
Wow.
emerges from the collective behavior of these interconnected loops and their spins.
So it's almost like a giant, very complex dance,
Yes.
with each loop playing a specific role in the overall choreography.
Exactly. It's a beautiful picture, isn't it?
It is mind-boggling.
It is.
But it's beautiful, and I'm starting to see how LQG is attempting to bridge that gap between the smooth space-time of Einstein's theory
Yeah.
and this quantum world where everything is about these discrete units and probabilities and things like that.
Exactly.
But okay, so how does all of this actually play out in the real universe?
Yeah.
What are the observable consequences of space-time being made of these tiny loops?
Well, that's where things get even more interesting, I think.
Okay, I am ready. Hit me with it.
LQG predicts some pretty radical things about the nature of area and volume.
Oh boy, here we go.
Are you ready?
I think so. Lay it on me.
So it says that area and volume aren't continuous like we normally think.
Okay.
They're quantized, meaning they come in these discrete, indivisible units.
Wait, so you can't have, half a Planck volume?
You can't... That's amazing.
Exactly. Just like you can't have half an electron.
Right.
You can't have half a Planck area or half a Planck volume.
So space itself is fundamentally chunky. That's not a good way of putting it.
That's a perfect way of putting it.
There's like a limit to how small a volume can actually be.
Precisely. And those chunks are determined by the spin network.
Okay.
So the area of a surface is determined by the number of loop lines that puncture it. And the volume of a region is determined by the number of nodes in the spin network that it contains.
So it's like each loop piercing a surface adds a tiny little bit of area.
Yeah.
And each node in the network contributes a bit of volume.
Exactly.
That is blowing my mind a little bit.
It is mind-bending.
We have gone from chunky smoothies
Yeah.
to a cosmic tapestry woven from loops.
With quantized areas and volumes, this is just the beginning of our LQG journey, isn't it?
Oh, this is just the tip of the iceberg.
Oh, boy.
There is so much more to explore,
I'm ready.
from the implications for black holes to the very nature of time itself.
I can't wait.
But I think we've laid a pretty good foundation for understanding the basics of loop quantum gravity.
Definitely. At least, I think we've gotten a taste of how LQG is trying to kind of rewrite the rules of reality at the most fundamental level.
That's right.
And I have a feeling this is just the beginning of a very exciting and probably very confusing
It will be.
adventure for us.
It definitely will be.
I am all buckled up and ready for more.
Excellent.
I can't wait.
I'm excited to share it with you.
Let's do it.
Okay, so we've kind of established this idea that space-time might be woven from these tiny loops.
Right.
And the way they connect that determines the universe's very structure. Pretty mind-blowing stuff.
It is.
But how do these loops actually behave? It's not like they're just static, frozen in place.
That's exactly what I was thinking.
Yeah.
It's like, okay, I can picture this cosmic tapestry.
Mm-hmm.
But a tapestry doesn't usually, change over time.
Right.
And the universe is obviously not static.
Yeah.
Things are moving around. It's expanding, evolving,
Absolutely. And that's where things get really, really tricky.
Okay.
Even for physicists who work on this stuff day in and day out.
I can imagine.
You see, one of the biggest challenges in LQG is understanding the dynamics of these spin networks.
Okay.
How they change, how they interact over time.
Right, because if everything is made of these loops, how do you even describe change?
That's exactly it. And that brings us to what's often called the problem of time.
Yes. I was hoping we'd talk about this.
Oh, it's a big one.
It's like, how do you even talk about time when your theory says it emerges from the interactions of these loops? It's like a chicken and egg situation.
You've hit the nail on the head, it really is, because time is one of those fundamental concepts in physics.
Absolutely.
But it's also one of the most slippery and confusing when we try to merge quantum mechanics with general relativity.
It's like they have two completely different ways of dealing with it.
They really do.
Like in Einstein's theory,
Yeah.
time is all woven into the fabric of space-time.
Mm-hmm.
It's relative. It can be warped by gravity.
Exactly.
But then you go to quantum mechanics,
Yeah.
and time is just this absolute external parameter.
It's ticking away in the background.
Right, like a metronome or something.
Exactly.
So is it fair to say that LQG kind of has to reinvent how we think about time itself?
You got it. That's exactly right.
Right.
LQG proposes that time isn't actually fundamental. It's
Sure.
not this independent thing ticking away out there.
So it's not like a separate dimension or something.
Not in the traditional sense, no.
Right.
Instead, time emerges from the relationships between the quantum states of the spin network.
Okay, so it's like a consequence of the dynamics of those loops, not a separate thing.
Precisely. And I think a good way to think about it is like the difference between a still photograph and a movie.
I like that.
In classical physics, time is like the frames of the movie. They're evenly spaced, moving forward at a constant rate.
Okay.
But in LQG, time is more like the flow of the story itself, emerging from the sequence of events, the connections between them.
That's a really, really cool way of looking at it.
It is. It's a bit mind-bending, but
It is.
yeah.
So time is like more of a verb than a noun in LQG.
I like that, yeah.
Like it's not a thing, it's a process. It's something that happens because of these loops interacting.
Got it. You're really getting it.
Okay, good.
Yeah.
But if time is emergent like this,
Yeah.
how do physicists actually study the dynamics of these spin networks?
Yeah.
Don't they need time as like a reference point
Right.
to describe how things change?
That's one of the central challenges. It's like trying to describe the plot of a movie without referencing the frames or the time code.
Yeah, you'd have to come up with a whole new way of talking about it.
Exactly. But physicists are clever.
Oh, I'm sure they are.
And they've come up with some pretty amazing approaches.
Okay.
One of the most promising is what we call spin foam theory.
Spin foam.
Spin foam, I know, more jargon.
Okay, that sounds even more abstract than spin networks.
It does sound that way.
I'm game. I'm ready.
Okay, so think of spin foam as a way to visualize the evolution of a spin network through something that's kind of like time
Okay.
in the LQG framework.
So it's like taking snapshots of the spin network at different moments.
Yeah, kind of.
And then connecting them in a way that shows how it's changing.
Exactly. Each face of the spin foam represents a kind of moment in the evolution of the spin network.
All right, I think I'm following so far.
And the connections between these faces, they represent the quantum transitions
Okay.
between different configurations of the network.
So is it kind of like those old flip books
Yes.
where you draw a slightly different picture on each page, and then when you flip through them really quickly, it looks like motion?
It's very similar to that.
Okay.
But instead of simple drawings, we
Yeah.
have these complex mathematical structures that represent the quantum states of the spin network
Okay.
at different stages in its evolution.
That's wild.
It is.
So physicists can kind of figure out how to flip through this spin foam.
Mm-hmm.
They can get a glimpse of how space-time itself changes over time, even without a traditional concept of time.
That's the hope.
That's incredible.
And by studying spin foam,
Yeah.
physicists can try to calculate the probabilities of different transitions between spin network states.
Okay.
And these probabilities, they're called transition amplitude.
Transition amplitudes, got it.
And those are kind of like the rules that govern how the universe evolves at this quantum level.
It's like they're creating a whole new set of rules for a reality we can't even directly observe.
Oh.
So, okay, I think I'm starting to get a feel for how LQG is trying to tackle this problem of time. It's almost like they're building a whole new language to describe the universe.
Yeah.
One where time is less of a rigid framework
Right.
and more of this fluid, emergent property.
I like how you put that.
Okay, good.
Yeah.
But then the big question, how do we know if they're on the right track?
That's the million-dollar question.
Oh, yeah.
And it's one of the biggest challenges facing LQG.
I bet.
Direct observation of the Planck scale is just way beyond our current technology.
So no super microscope to zoom in on these loops and see if they're really there.
I wish it were that easy, but
I know.
don't despair. There are some very clever physicists out there
Oh, I'm sure.
who are looking for indirect ways to test LQG.
Okay, so what are they looking for?
They're searching for these subtle effects
Mhm.
that these quantum fluctuations in spacetime
Mm-hmm.
might have on things we can observe,
Okay.
like light from distant galaxies.
Right.
Or the cosmic microwave background radiation.
So it's kind of like looking for the ripples in a pond, even if you can't see the pepper that caused them.
That's a great analogy.
Okay, good.
It's a long shot, absolutely.
Yeah.
But if we find those ripples, it would be a huge step towards confirming that LQG is more than just a beautiful mathematical theory.
Right.
It's a description of how reality actually works.
Okay, well, I'm definitely ready to hear more about those potential ripple effects.
Okay.
Where should we dive in next? Okay, so we've talked about these loops and the spin networks and even spin foam
Yeah.
and this whole mind-bending idea that time itself emerges from how these things interact.
Mm-hmm.
But I keep coming back to this question of actually testing LQG.
Right.
It just feels like we're talking about something so far removed from, our everyday experience.
Yeah.
How do we bridge that gap? How can we possibly observe something happening at the Planck scale?
It is a huge, huge challenge. We're trying to probe the universe at the smallest possible scales imaginable, where quantum gravity is thought to be dominant.
Right.
But as you said earlier, there might be these subtle ripple effects that we could actually observe, even if we can't directly see those loops.
Okay, so you mentioned the cosmic microwave background radiation, the afterglow of the Big Bang.
Right.
How could LQG have left its fingerprints on something that happened billions of years ago?
Well, that's actually one of the most exciting avenues of research in this whole field.
Really?
Yeah, the idea is that these quantum fluctuations in space-time, the ones arising from the loops and their interactions, might have left a tiny imprint on the cosmic microwave background.
So it's like those ripples on a pond, but on the most ancient light in the universe.
Exactly.
What would those ripples actually look like if we could see them?
So they would be incredibly subtle variations in the temperature and polarization of the cosmic microwave background.
So like tiny hot spots and cold spots?
Yeah, think of it like that. Yeah. Tiny hot spots, cold spots, or even swirls in the polarization pattern.
Wow.
That wouldn't be there if space-time were perfectly smooth.
Okay, so that's like some seriously high-precision cosmology.
Oh, absolutely.
To be able to detect something like that.
Yeah.
Are scientists actually seeing any hints of these LQG ripples?
Well, that's the million-dollar question.
Yeah, good.
It's still very much an open question.
Okay.
There have been some, tantalizing hints, but nothing conclusive yet.
I see.
The problem is there are other possible explanations for those tiny variations in the cosmic microwave background.
Yeah, there's a lot going on in the universe.
Exactly. So distinguishing between the signal from LQG and these other sources of noise is incredibly difficult.
So it's almost like trying to hear a whisper in a crowded room.
That's a perfect way to put it. It really is.
It must take some incredible instruments and, really clever data analysis to even attempt that.
It absolutely does, but physicists are,
They're up for the challenge.
They are. They're working hard, developing new techniques, refining their models to try to tease out those signals.
Okay, well, that's really exciting.
It is.
And you mentioned that the cosmic microwave background isn't the only place where LQG might leave its mark.
That's right.
So where else are scientists looking?
Black holes.
I'm hoping you'd say black holes.
I figured you would.
They're kind of the ultimate test for any theory of gravity, right?
Exactly. They push space-time to its absolute limits.
Yeah.
And LQG makes some very specific predictions about how black holes should behave.
Okay, so give me the LQG take on black holes.
All right.
What's different for the picture we get from Einstein's theory?
So one of the biggest puzzles in black hole physics is this concept of entropy.
Okay, entropy, that's a measure of disorder or randomness, right?
That's right.
And you see, according to classical general relativity, black holes should have zero entropy.
Why is that?
Well, because black holes were originally thought to be incredibly simple objects with all their mass collapsed into a single point. Right, a singularity.
Exactly. So it seems logical that they wouldn't have any entropy, no disorder.
Right, because it's just like one thing.
Exactly.
But I have a feeling LQG has something to say about that.
It does. Remember how we talked about area being quantized in LQG?
Yes, with those spin network lines puncturing a surface.
Exactly. And that has some really profound implications for black holes.
Okay, I'm listening. Because black holes do have a surface, right?
They do.
The event horizon.
The event horizon, the point of no return.
Beyond which nothing can escape, not even light.
Exactly.
Okay.
And in LQG, the area of that event horizon is determined by the number of those spin network lines that intersect it.
So each puncture adds a little bit of entropy to the black hole.
Exactly. Each puncture contributes a tiny bit.
Okay.
And then when you add up all the contributions from all those punctures, you get the total entropy of the black hole.
Okay, so the more punctures, the more entropy.
Makes sense.
Right. It does.
But here's the amazing part. When you actually do the calculations in LQG, the entropy you get matches perfectly with the famous Bekenstein-Hawking formula, which was derived using a completely different approach based on thermodynamics and quantum field theory.
So LQG not only agrees with what we already know about black holes, it actually gives us a deeper explanation for one of their most mysterious properties.
Exactly. It really does. And that's seen as one of the biggest successes of the theory.
That's incredible.
It is.
It suggests that we might actually be on the right track with this whole loops and spin networks idea.
Yeah, it's a hint that these might really be the key to unlocking the secrets of quantum gravity.
This has been an amazing journey exploring this strange and beautiful world of loop quantum gravity.
Yes.
We've gone from, chunky smoothies to cosmic tapestries.
Yeah.
From this problem of time to the entropy of black hole.
It's quite the adventure.
It really is. And it's mind-boggling to think that these abstract concepts, these loops, these networks, might actually be the key to understanding the very fabric of reality.
It's a testament to the power of human curiosity.
Absolutely.
Our drive to understand the universe, even at these incredibly fundamental levels.
And even though LQG is still, a work in progress.
Oh, absolutely.
There are many challenges ahead.
Yeah.
It offers us this glimpse into a reality that's, far stranger and more wonderful than we could ever imagine.
It really is.
I completely agree. It's a reminder that there's so much out there still to discover. So many mysteries yet to be unraveled.
Yeah.
And who knows what other kind of mind-bending ideas await us as we continue to probe the deepest depths of the universe.
That's the beauty of science, isn't it?
It is.
There's always another layer to peel back, another question to ask.
Exactly.
And each answer just leads to more questions.
It does. It always does.
Pushing us further on this quest to understand the cosmos.
And our place within it.
Exactly.
Well, I think on that note of cosmic wonder, it's time to wrap up our deep dive into loop quantum gravity.
I agree.
To all of our listeners out there, thank you so much for joining us on this incredible adventure.
Yeah, thanks for listening.
We hope you've enjoyed stretching your brains a little bit.
Yeah.
And exploring the frontiers of physics with us.
It's been a pleasure.
And remember, keep looking up, keep asking those big questions.
Yeah.
And never lose your sense of awe at the beauty and the mystery of the universe.
Couldn't have said it better myself.
Thanks for joining us.